right, this is Stephanie Washer for the IPv6 addressing portion of Module 3. So we're at 3-2B, Cengage MindTap Network plus Guide to Networks for my PCT 110 Network Essentials course at Rock Valley. So we started talking about IPv4 addresses, and we went through quite a bit with IPv4 addressing. And we know that IPv4 addresses have 32 bits. That's not very much, right? So we have 4.3 billion addresses that we can assign. With all of the items and devices, everything that's connected, our IP addresses were running low. Even using tricks like private IP addressing and network address translation, we're just running low. So IPv6 standards were developed so that we can have more public IP addressing. And it's still, again, at the network layer. Both of these are at the network layer, layer 3. So whether it's IPv4 address or IPv6, they're still network layer addresses, layer 3 addresses. But IPv6 just worked to improve on any of the items that were disadvantages of IPv4. So we've got more addresses. We are now, instead of binary, we're in hexadecimal. So we've got 128 bits, 8 blocks. So these are called quartets. So we've got hexadecimal numbers separated by colons. So we've got 1, 2, 3, 4, 5, 6, 7, 8. And so since there are 8 blocks, there's 4. Each one of these is called a quartet. So we've got 8 blocks or quartets. Each block is 16 bits long. So we've got, since it's hexadecimal, it goes from 0 to 9, and that or A through F. So we've got 16 numbers in each one of these. So it's 16 bits. So the first block of, like, so this 2001, for example, it's actually written like this in binary. So it's 1, 2, 3, 4. So it's 16 different bits in binary. So it's 4 binary numbers. So it's 16 bits long. So each one of these in binary is 16 bits long. It's a lot because it's 128 bits total. But that means that we can actually give out more numbers, right? So they're so long, we have to figure out, well, we need shorthand notation. So we're gonna go through how to shorten those numbers as well. And one of the ways to shorten them is to eliminate the double zeros. So we've got, here is a group of zeros, and then here's a group of zeros. And what I like to do is I like to look and see where there's more zeros. So like here, you can use the double colon, and it tells the system that there's all zeros in between there. But you can only do that once. You can't do that multiple times. You can only do that once. So what I like to do is, because there's only 4 zeros here, but there's 8 zeros here, that's where I like to do the double colon. And so the system will figure out how many zeros need to be put in there. If we did that twice, it wouldn't know whether to put 8 zeros here or 4 zeros here or vice versa. So it doesn't know, it can't be precise when you use that colon twice. So you can only use it once. So the preferred method is the second one, because then you're doing more numbers in the shorthand, the fewest zeros, so you can make it the shortest. It's kind of like in math, making it the smallest. So here's some terms. There's some other terms. So we've got a link, sometimes called the local link. And so any LAN, or, you've got routers in between. There could be a couple of people, so your neighbors, 2 or more PCs or nodes or whatever, can be on that same link. And the network is dual stacked if it's using both IPv4 and IPv6, which a lot of them probably are doing. I know a lot of internal networks might be using IPv4, but they might have to use IPv6 with their ISP. If you're doing dual stack, you can also do what's called tunneling. And that is just transporting IPv6 packets over IPv4 network. In my Cisco class, we talk a lot about that. And then the last 64 bits. So in the IP address here, I'm going to go back up here. So we've got 128 bits total. And in the first 64 bits, that would probably be here. So the first, first 64 bits, those are like uniquely identified, and then the last 64 bits are the interface ID. So the last 64 bits or the last 4 blocks are the interface ID or interface identifier. And then the first 64 are pretty much set by the local link. So we have, and it'll be explained a little bit more here because we'll talk about unicast address, global address, the link local address, and kind of how those are configured. So we do have our different IPv6 addresses. So we have a unicast address, and that is a single node on a network. So the unicast addresses can have, we can have it where the first 64 bits are link local, and the last 64 bits are interface ID. So we have FE80 /64. And so that /64 is our CIDR notation. And this one doesn't have an assigned IP address yet. And so that we'd have to set the interface ID, probably just like :1. And so that last 64, but it would be in that last 64 bits, if that makes sense. So the first 64 bits are the link local address, but you still have to have this interface ID set to be able to put it on the interface. And so if you were looking at the global address, so I just went over the link local. If you're looking at the global address, we have the first 3 bits, then we have the global routing prefix, we have the subnet ID, and then we have the interface ID. And then the loopback address is just 127 bits, and it's all zeros, and really it's just :/0. And we'll go over that. :1/128, sorry about that. So the global address can be routed on the internet, similar to the IPv4 address. They almost always begin with 2000 :/, and it's always going to begin with that 2000. But there are other ones, but the /3 indicates those first 3 bits are always the same. So that's what that means. And then we've got our subnet ID. So notice the 16 bits reserved for the subnet ID can be used to identify. So if we look up here, those 16 bits can be a subnet that we can set up. Generally, most of the time, I haven't seen anybody really use the subnet ID, but you can if you want to. Link local address, that's always FE80. So if you ever see FE80, that's going to be link local. They have the example here. And so /10 just means that that's reserved for FE80. And then the remaining are all zeros. Therefore, the link local is always FE80 :/64. And if you actually assign an address to it, you're going to put it like usually I'm just talking from the Cisco world of things. So the gateway is usually FE80 :1, and then you could do any other number for the nodes, but they have to be a different number. So like FE80 :1 would be the router or your gateway, and FE80 :2 could be your switch. FE80 :10 could be your PC. So that's if you're setting them up statically. So and then the loopback address, :1/128. So it's just 127 zeros followed by a 1 and is written as :1/128. And then we get our multicast addresses and the anycast. So what happens is we have a multicast address where we can send to multiple people on the network or multiple nodes on the network. Anycast address is just going to be multiple destinations. It's similar to the broadcast. But broadcast is sent to everybody. Anycast is a little bit more it's not the same as broadcast. It's not sent to every node. So IPv4 broadcast is sent to every node. Anycast is just sent to the closest destinations. So here's an example. So we've got broadcasting, multicast, anycast, unicast. So broadcasting sent to everybody. Multicasting, certain people. Anycasting is, again, it's sent to certain ones. So we've got, and then unicasting. So really, we've got multicast flooding. So you can multicast a group or a single IP address, and there's no associated MAC address with that IP address. So you can multicast flood, and it just floods all interfaces, which honestly then defeats the purpose of that. So then you can change that, or you can fix it by using your Internet Group Management Protocol, or IGMP. So you can use that to fix it. And then here's just the different prefixes. Table 3.3, here's the different IPv6 prefixes. So global unicast is 2000:3, so the first 3 are fixed. And then FE80:10, so we've got our link local unicast, so the first 10 bits are always the same. Unique local unicast, and then we've got these two, FC00, FD00, and then the multicast is FF00. So, multicast, we always want to look through those. You can do ipconfig just like I did in IPv4 video, and you can see your IPv6 address. And it just depends on what you're using. And this is the VirtualBox one, and so if you have VirtualBox up and running and going, but you can see the IPv6 there. This picture takes forever to load. The IPv6 here, and then the IPv6 for our wireless. So, and then auto configuration, we can set IPv6 auto configuration. So stateless address auto configuration, I call it SLAC, and it's similar to the PIP address in IPv4, but we have here where we're going to describe exactly how it works. So we have this stateless address auto configuration. So what's going to happen is the computer is going to create its IPv6 address. It's going to use the FE80 number. It's going to use that link local. It's going to use that prefix. And depending on how the OS is set up, the last 64 bits are going to be generated in 2 different ways. So the 64 bits are randomly generated, and it's a temporary IP address. It's not registered with DNS or to generate a global address for the internet. So it changes to help prevent hackers from discovering the computer. So this is a default method used by Windows 10. Or there's the 64 bits are generated from the network adapter's MAC address. So it can, our MAC has 48 bits, and it's converted to a 64-bit standard, or the extended unique identifier 64 standard. So to generate the interface ID, the OS takes 48 bits of the MAC address, inserts a fixed 16-bit value in the middle, and then inverts the value of the 7th bit. So that's how it generates the MAC, then network adapter address from the MAC address. So then what'll happen? So step 1, randomly creating an address. Well, one is randomly generated, the other is using the MAC address. And then step 2, that computer then is going to make sure that it's a unique address on the network. So it's going to send out, and then it's going to look and see if there's a duplicate. And if there's a duplicate, it'll try again on the randomly generated. Step 3, the computer asks if the router on the network can provide configuration information. So this is a router solicitation or an RS solicitation. And if the router responds with DHCP info, and so the router will respond with a router advertisement, or RA message. And it can be IP address of DNS server, network prefix. It can be many different things. Not many different things, but it can be a couple different things. And so it can start what's called prefix discovery, and the computer then uses the prefix to generate its own link local or global IP address depending on what that router advertisement states. So since the computer can generate its own link local or global IP, the DHCP v6 server, so an IPv6 DHCP server, serves up only global IPv6 addresses. So the link local addresses aren't served up by the DHCP v6 server, it's only global addresses. So web servers, DNS servers can receive their static IPv6 addresses from a DHCP v6 server. So anytime you see v6, it's IPv6 stuff. And you'll see v6, here or there, and it's the IPv6. And on a larger network, IP addressing can really be a management issue. So IP address management system, whether it's a standalone product or what, Windows Server or wherever they get it from, they're going to use some sort of IP address management tool that can automatically detect all of this information. So it can detect IP address ranges, assignments, reservations, exclusions, all of that, and integrate it into its DNS. So it will work through all of that. This next portion is on ports and sockets, and we'll go over that in the next video.